Hi. So this is the this operating system that I made for my Duke of Edinburgh award. So firstly, we'll start from the beginning. So when you start up the operating system, it uses this crate bootloader, made by Philip Opperman, um, to essentially boot into the OS. And when it first boots, it looks for this macro, which essentially sets the entry point. Now, what we do here first is we initialize the interrupt descriptor table. Now, what that is a table it's a table that essentially tells the kernel and tells the system that when you when you get a certain type of signal, that refers to the IDT, uh, well, it does something, right? So that's how it works. What we do here first, is when we do init IDT, we initialize the interrupt descriptor table. So what that is this. Now, first we initialize it from this. So this is a description, and you can see how the first 32 entries are used for CPU exceptions. So we set dot breakpoint, right? So this is referencing a parameter. So dot breakpoint, and then dot double fault, dot page fault. Now the reason that we use an index here is because this is actually aligned 16, repr aligned 16, repr C. I don't know entirely what that means, but I know it means that when you do that, you can reference this. So we have interrupt indexes here. So an enum here. So timer, keyboard, and then we implement as u and as u size. So these are just functions which return the value of this. So timer is equal to pick one offset. So a PIC is a programmable interrupt controller. So this is 32, and it says here the first 32 entries are used for CPU exceptions. The remaining entries are used for interrupts. So normally, the first interrupt, hardware interrupt rather, is the timer. And what we do here is we send a notification to the PICs that the interrupt's ended, right? We've done everything we need to do, because when an interrupt is essentially it's a stopping of the CPU's cycles, and we say to the CPU, hey, stop whatever you're doing and do what I want this to do now, which means it runs asynchronously. So when we've done everything we need to do through the interrupt, we tell the PICs, hey, we're done. And then this says what type of interrupt it is. Now the keyboard, we open a port. This is the keyboard interrupt. So every time we click a key, it sends an interrupt towards the PICs and then into the operating system to do things. So here we have the scan code, 14, which represents backspace. And a scan code is essentially the raw bytes, I think, of it's the data that the keyboard sends. So 14 is the key down for backspace, and 28 is a key down for the return key or the enter key. Now, here we can see that it's referencing this thing called a text buffer. We'll get to that in a moment. So after we do that, we initialize the global descriptor table. Now what that does is it's essentially I don't know what it is. What? Okay. Look it up because I'm not very good at explaining this stuff. So structures, global descriptor table. Here we go. Yeah. So a GDT is used for loading a TSS, which you see here, task state segment, which is essentially what we use to handle double faults. Well, that's what I've used it for. You can see here, we set some registers and load them. Yeah, so yeah, so yeah, so the GDT is used for switching between user and kernel mode. I don't do that. I haven't worked nearly as much on this operating system as I could have to do that. Obviously, I've worked a ton, but yeah. So that's what the GDT is. Here, I'll pull up the official definition. Here, so yeah, a GDT is essentially a table, and it's used. Here we go. Yeah, so it's a data structure which contains entries of memory segments. So here we have a certain segment dedicated to a task state, so a task state segment. So it tells whether it's normal or double fault, I think. Yeah. Anyway, after that, we initialize the PICs. So what that is, we'll go over here. It's essentially this mutex wrapped type chain PICs from this crate PIC 8259. Here. So here, yeah, so it's this crate, and essentially what that is it emulates a programmable interrupt controller. So it just declares a new, or I guess initializes a new chain PICs. Yeah, okay. Now after that, we start up the memory. We declare a physical memory offset, which is a virtual address. Well, a new virtual address of the physical memory offset defined in the boot info. And then we declare a mapper, which is this. So if we go to memory and we go to init here, we initialize level 4 page table, which is essentially the outside page table. If we go here, oops, okay, yeah, so we have page tables. The way it works is you have a page table here which has a bunch of entries, and you take one of these entries, and this entry might point to a level 3 page table, which might have an entry which points to a level 2 page table, right, and so on and so forth, all the way down to level 1. And this just declares a level 4 page table, which is the highest level, and then it returns the offset, which is from the physical memory offset. Yeah, and then we declare a frame allocator. So this is essentially a frame allocator from the memory map in the boot info, and then the allocator initializes the heap, but this returns an option value, which means, option value, which means it either returns okay, is it? No, yeah, it might be result. It's one of them. Anyway, expect happens when this doesn't work, and normally it would panic, but here what we do is we use .expect. So if it panics, we, I guess, print this message, and then the code panics, and then this just draws the prompt. So see if I can run it now. Okay, I throw update Rust. I haven't used the machine in a while, so I'll go do that. Okay, so hopefully this works. I'm installing Q now. So yeah. Now, while it's installing, we can go over more of what I've done. So the first thing I really did was develop the VGA buffer. So this really starts, it's quite linear, the code, I would say. So first what we do is we create a bunch of structs, which correspond to, screen characters. So this is the ASCII character represented in a byte, and then a color code. So these colors. Then we make a buffer. So as it says, screen var, repeated across buffer width times. So that's this first list, and then first array, and then repeated down buffer height times. So we have an 80 by 25 screen, and then we create a writer struct, and then we have the cursor column, cursor row, and then background, foreground, and background color, the full color code, and then the buffer. Now what we do here is when we declare the writer type, well, I guess the static writer, we have the foreground color, which is yellow, and the background color, which is black. I chose yellow because it looks cool, and I like it better than white, which, to be honest, is kind of boring. Anyway, what we do here is we declare the buffer. So we declare the buffer as a borrowed mutable pointer, and this pointer is this memory location as a mutable pointer to the buffer. So it points to this memory location, but when it points to this in the code, it thinks that the this buffer is actually just this, because that's what it is, but it's a pointer. So not the actual thing, as I learned. All right, give me a second. Okay, so I've installed Kimu, and we're gonna go run the program now. So when it builds, the first thing it does is it compiles core. So that's the core library of Rust. Takes a while. Now essentially what you're gonna see is when Kimu pops up, you're gonna see this. Now this this macro references a macro declaration here, which references this hidden function. And what this does is it declares that without interrupt, so to prevent a soft lock of this where this is locked, and then before it's unlocked, it's locked. Well, basically, to prevent a soft lock, it uses, I forget what this is called, a closure. Yeah. So this closure, and then it uses, and then it references this function. Now there's a bunch of functions in here. A lot of them aren't being used. So, move cursor I don't use, or I'm not using, because I've scrapped using arrow keys. They're too complicated, and there's a lot of code that I have to write. That's pretty much unnecessary for such a relatively unneeded function. So focused my efforts more on developing memory. Yeah, so here's draw cursor, and then down here is draw prompt. So this references the prompt in lib.rs. So this is another static variable. Sorry, this is another static variable, and it sends the row to be self.cursor. So if it's running here, so you can see I can type from keyboard interrupts, and I can't delete past the prompt, right? Which is what you see in something like git bash. And I've even added a few commands using a text buffer. So the way that this works is when you type, every time a key is pressed, I'm pretty sure it's in this file. Oh, it's not. Interesting. So anyway, so we have a struct here which has information. And you'll notice that this vec type is like a list, but in languages such as Python, you'll know that lists aren't really, they can have a variable size, unlike arrays in Rust, right? So if I were to declare this, I can't just have, I can have it like that, but ideally when you declare an array, you declare it like that, right? So this is now a sized array, and this size can't be changed, right? So I'm using a vector, which you only get from this allocate, and as you see here, the Rust core allocation and collections library. So I've implemented this using a fixed size block allocator. So the way it works is if we open up MS Paint here, imagine you have the this, which is the let's say this is the heap, right? So not the stack, this is the heap. Now when I want to allocate something to the heap, let's say I have a value which is 6 bytes, right? Now as you can see here, the largest block size is 8. So instead of figuring out, you know, if I only wanted to put one thing onto the heap, I could just allocate this 6 as 6, right? But then a problem arises, right? Because the heap is divided, because I want to divide the heap well, relatively evenly, right? Let's say I have another one of size, let's say 13, right? So this is 19 bytes, and then I have the rest of this. So let's say this is actually 12, right? So 6 and then 6, right? The way it works is as time goes on, the memory is going to be divided into really small chunks. So the way we prevent that is by using fixed size blocks, right? So instead of having like variable block sizes, we have fixed block size, right? So we have, if we want to allocate 6, we have a block size of 8. So we have 6 plus 2, which makes 8, right? And this is really, really fast, but the only downside is, in the worst case scenario, right, we would be wasting half our memory. So we would only be able to use 8 gigs. But obviously that wouldn't happen, because that's a really, really rare thing to occur. And underneath the fixed size block allocator, our fallback allocator is linked list allocation. The way this works is, let's open Paint again. Oops. Let's open up Paint again. Sorry. So the way this works is we have our heap, and we have a few, let's say we have a few blocks here, right? Now the way this works is at the end of each block, so we have metadata to the list node. So you have the size of the list node, right? Say that's here, and then you have a pointer to the next list node, right? Now the reason that this is an option is the point, if we're dealing with this, right, you might have a pointer, or you might have the next pointer, right? But this is just a none. This is a it would be none, right? Because there is no like next block or next node, right? And then we have a few functions for the implementation of list nodes. So a new function, and then get the start address and end address, and then a bunch of, you know, other stuff here, which is pretty difficult to explain and not really needed. So that's how the memory works. And then I have a few commands. So as you can see, I type clear and it clears the screen. What else do I have? So that'll be in text buffer here. Yeah, so that's how vec works. That did get a bit sidetracked. Anyway, if we go to process command, we'll have all the commands down here. So we have echo. So if we want to echo hey, right? At the moment, it'll echo quotes, and I don't have control C implemented, so if I echo nothing, it'll echo nothing. Like, if I open up a new instance of bash, as you can see, that's how it works. I have who am I, so at the moment the default user is user, so who am I, user, and then I have I am, which sets the user. So that's my name, I'm Leon, hi. So now Leon, right? And then probably the coolest thing that I did, because a lot of this is really boring. Once you get past you know, things working is always nice, but it breaks a lot of the time. I would say the coolest thing I did was develop this. So if we go into process command, we go to math. This is what I did here was I developed a lexical parser. Really cool. So the way it works is first when we run the command math. So I'll show you it works, right? 1 + 1, 2. 1 times 1. Oh, math. 1 times 1, 1, right? And I even implemented brackets. So math 1 + 3 times 3, 12. So that's 4, 12. And then math 1 times 3 plus 3, 6, right? So, you know, pretty cool. So, the way it works is if I enter something like invalid, right? So I do that, right? Well, I don't know what that was. Can I do that? Yeah, there we go. So invalid arguments works sometimes. Obviously, it's not perfect. I think I'm definitely going to be developing this OS after I submit the project. But yeah, this is probably my favorite thing about it, is that I have a lexical parser. It was a bit of a sidetrack, mostly procrastination, because I was super tired of working on input and output. So I developed this and then extrapolated all of the port IO and file system development to another branch. So yeah, tokenize, yeah, a bunch of functions. So firstly, what we do is we separate it out into tokens, return a list of tokens, which we see, where is it? Here. So we parse essentially the expression and then tokenize the expression, and then if the tokens isn't empty, so if I go here and just do that, expected greater than 1 args got 0, so that's what we do here. Where is it? Yeah, here. So if it's not empty, then parse the tokens, evaluate the tokens, and then we return the evaluation as a string, as bytes, to a list. So a list of bytes, pretty sure this just returns, yeah, an array. So I want it as a vector, because that's what this is. Yeah, there we go, evacuate. And then we have flags. So this is another thing that I made. What's really nice about this is when I designed the command system, I made it so that it would be able to be extended. So we have result flags here, and at the moment there's only 2, so contains result and clear screen. So they're both boolean values, and yeah, you know, this is for testing. So serial printing, and then just implementations of macros right here. You know, and I think that's it, right? The other commands are pretty simple. Echo just takes the text, whatever's after echo, and then returns it. Clear screen, well, clear screen, right? Yeah, so that's pretty much it, I think. If you have any questions, let me know. I think that's a pretty apt description. Obviously I have a devlog here. And then, yeah, there's some leftover bootloader stuff here that I was trying, but realistically, you know, if I want to develop a bootloader, I'm gonna do it far, far in the future. You know, I use the bootloader creator now. Yeah, that's pretty much it. See ya.